Bena is organizing his birthday party and has decided to invite all the people in the class. The class, however, has too many nerds who are too shy to directly approach people that they don't know. Bena wants everyone to meet each other in the party, and he starts investigating conditions that guarantee this. First, he transforms the social network in the party into a graph where the people are vertices and two people are connected if and only if they're friends. Then he comes up with the following condition, which we'll call the general friendship condition. Every pair of people, or vertices in the party, have at least one mutual friend, or neighbor. This condition is useful since if any two people don't know each other, then the mutual friend can introduce the two people to each other, and so everyone gets a chance to meet. Bena is now curious about graphs with the general friendship condition. How do they look like, and can we classify them? In this video, we'll give a partial answer to this question by showing examples of graphs with the general friendship condition, then covering a specific case of these graphs, and finally discussing a generalization of the specific case. Now we look at some examples of graphs with the general friendship condition. To start off, we look at the complete graph. Every pair of vertices in this graph has at least one mutual neighbor, since everything is connected. Our second example is the octahedral graph. We can see that it also satisfies the general friendship condition, which we can verify visually. In this animation, each pair of vertices, in red, has a mutual neighbor, in green. Our third example is the graph from homework 10, in which we place 17 vertices around a circle and connect vertices that are distanced 1, 2, 4, or 8 away. This also satisfies the condition, as we can quickly verify. From these examples, we can see that the category of graphs with the general friendship condition is broad, so we're going to focus on a specific case of this condition. One natural way of specifying the general friendship condition is to consider the minimal case. In other words, instead of having multiple mutual neighbors, consider having exactly one mutual neighbor. We'll call this condition the friendship condition, and call graphs that satisfy this condition friendship graphs. Now we look at some examples of friendship graphs. The complete graph K3 is the simplest such example. Now from K3, we can construct a bigger friendship graph through adding another K3. Take a few moments to see why this graph satisfies the friendship condition. Now, out of this graph, we can build a bigger friendship graph by adding another K3. And we can construct an even bigger one through the same process. We can repeat this process to obtain an infinite family of graphs known as windmill graphs. This family of graphs are all friendship graphs, and as it turns out, they're the only such graphs. In other words, every friendship graph is a windmill graph. We'll prove this theorem in two steps. We first prove our lemma. If a graph satisfies the friendship condition, then it has a vertex v, which is connected to every other vertex. Such a vertex v is known as a popular vertex. We then use the lemma to prove that every friendship graph is a windmill graph.
To prove the lemma, we proceed by contradiction. Let G be a counterexample, that is, a friendship graph with no popular vertex. We claim the following. Claim 1, G is a regular graph. Claim 2, if G is a k-regular graph, then n equals k squared minus k plus 1. Claim 3, if G is a k-regular graph, then k equals 2. Notice that this implies a contradiction, since plugging k equals 2 into claim 2 gives us n equals 3, which means G equals C3, which contains a popular vertex, so G would not be a counterexample. Let's first prove claim 1. First, fix non-adjacent vertices u and v. We will show that the degree of u is the degree of v. Let u have k neighbors, denote them with w's. By the friendship condition, u and v must have exactly one mutual neighbor. Without loss of generality, let it be w2. Likewise, u and w2 have exactly one mutual neighbor. Let it be w1. The mutual neighbor of v and w1 is w2. Next, consider the mutual neighbor of v and w2. If it is any of the w's, then we violate the friendship condition, since u and v have multiple mutual neighbors. Thus, there must be a new vertex Z2, and so on. We have found k neighbors of V, namely W2 and all of the Z's. From this, we can see that the degree of V is at least the degree of U. By symmetry, we can argue the opposite, that the degree of U is at least the degree of V. Thus, the degree of U equals the degree of V. For the other vertices, we can always find a non-neighbor, since we assume that there is no popular vertex. Thus, the same argument can be used to show that every vertex has degree k. Claim 2 can be shown by a simple counting argument. Let U be a vertex in the graph. Count the neighbors of U, then count the neighbors of those. Since we assume G is k regular, there are k squared many. Since each vertex has exactly one neighbor with U, this counts all possible vertices, but overcounts U k times. Thus, we find that n equals k squared minus k plus 1. Claim 3 arises from a neat trick using the adjacency matrix. Recall that the adjacency matrix A of a graph is a matrix whose ij element is 1 if vertices I and j are adjacent, 0 otherwise. For our graph G, the adjacency matrix looks something like this. Since we assume G is k regular, there will be k occurrences of value 1 in each row and column. If we square A, we get something like this. You can verify this using matrix multiplication, but note that the main diagonal consists of all k's because G is k regular, while the off-diagonal entries are all 1 by the friendship condition. We can compute the eigenvalues of A squared. By claim 2, k minus 1 plus n becomes k squared. This helps us find the eigenvalues of A. Take the sum of the eigenvalues. This equals the trace. Also, the trace of the adjacency matrix is 0, so we get an equation for k. We skip the details, but it turns out that the only solution is k equals 2, proving the claim. As a side note, while every friendship graph has a popular vertex, not every popular vertex is in a friendship graph. For example, a popular vertex exists in the star graph, which is not a friendship graph since there are no two vertices that share a common neighbor.
Now we use the lemma to prove the second step. We first assume that G has the friendship condition. Then, by the lemma, we know that G must have a popular vertex P. Now let V be any other vertex in the graph. By the friendship condition, we know that P and V must share a neighbor, U. Now we know that any two of P, U, and V have at least one neighbor. And for them to have exactly one neighbor to satisfy the friendship condition, U and V must be non-adjacent to the rest of the graph. We can keep repeating this argument with the rest of the vertices of the graph to conclude that G is a windmill graph.
We finish characterizing graphs where pairs of vertices have exactly one mutual neighbor, but what if there are multiple mutual neighbors? For example, the complete graph with n vertices is a graph where each pair of vertices has exactly n-2 mutual neighbors. The condition that every pair of vertices has exactly L common neighbors is called the L friendship condition, and graphs with this property are called L friendship graphs. If L equals 1, then we recover the friendship condition that we just discussed. For L at least 2, every L friendship graph turns out to be a regular graph. Let's return to planning Baina's birthday party. Recall that we want the party to be fun, and we want each pair of people to have some mutual friends in common. If each pair of people has exactly one mutual friend, then we get the friendship condition, and the friendship theorem applies. This means that the social network is a windmill graph. On the other hand, if each pair of people have exactly L mutual friends, for L at least 2, then we get the L friendship condition, and our results give us unfortunate news. The social network will be a regular graph. Despite Baina's high expectations, his birthday party will only be regular.